This is B. Naresh, working as Assistant Professor in AC Department. Today's topic is analysis of CA amplifier with emitted resistance using low frequency model. Let us consider for amplification, we observe that common emitter configuration is more suitable based on the gain factor of the configuration. So hence, here I use this common emitter configuration with emitter resistance that is represented as R. To design an amplifier, we need to show that the emitter base junction is forward bias and collector base junction is reverse bias. Let us consider to design the common emitter amplifier. I use the NPN transistor, means this is collector terminal, base and emitter. In a common emitter configuration, emitter is common for input side and output side. From that, the base terminal is acts as input terminal and the collector terminal is acts as output terminal. The collector is made with N-type material and the base is made with the P-type material and emitter is made with again N-type material. Hence, this transistor is NPN type transistor. Now, I use the self-biasing method to make the emitter base junction is forward bias and collector base junction is reverse bias. And by using this emitter resistance, and with respect to this emitter resistance, it is to stabilize the DC biasing. So if the DC biasing is stabilized, then automatically the Q point is also makes the stabilized. So if the Q point is stabilized, and that should be located in an active region, and we can use that configuration is for amplification process. For this case, let us consider if the VCC is increased here and the voltage drop across the resistance or collector resistance is also increases. Why? Because of the collector resistance is also, the collector current is also increases. If the collector current is increases, the voltage drop across this RC resistance is also increases. When the collector current is increases, then we know that the current flowing across this emitter resistance is represented as emitter current, that is IE. Hence, IE is also increases. If emitter current is increases, the voltage drop across the emitter resistance is also increases. And we know that the potential difference between this base and emitter terminal is represented as VBE. Let us take this is the VB node. And from this, we know that from the definition, VBE means the potential difference between base and emitter. If you want to write the base voltage, it should be from the circuit. We can write like VE plus VB, means the voltage drop across the emitter resistance along with the potential difference between base and emitter terminal. And this emitter resistance can be used to stabilize the Q point in terms of the biasing voltage and in terms of the temperature dependence parameter. So when the biasing voltage is increases, when the VCC is increases, it increases the collector current, hence the voltage drop across this collector resistance also increases. Due to increase of collector current, it increases the emitter current. Why? Because of we know that IE is represented as IB plus IC. So from this relation, if the collector current is increases, hence the emitter current is also increases. And due to this increase of emitter current, the voltage drop across the emitter resistance is also changes. Hence VE is changed. And due to the self-bias configuration, and at the input side, that self-biasing or a voltage divider network to compensate this change in voltage to stabilize the DC voltage or to stabilize the operating point. So from this emitted resistance across the emitter terminal. Now we are going to design a low frequency model or a small signal frequency model. Let us consider, and this is a small signal model for a common emitter amplifier without emitter resistance. Means the emitter is directly connected to the ground terminal. And from that common emitter configuration with the emitter resistance is 0, means without emitter resistance, and is showing that a small signal model for common emitter amplifier. In this case, let us consider, and up to this point, this is two-port model network. So if it is a common emitter is a common for input side and output side. Base is acts as the input side. Collector is the output terminal. From that, here I consider this approximate model. So here I consider that approximate model. Why? Because of that, we know that 1 by HOE is much greater than of ZL, or the HOE times of ZL is less than of 0.1. Then we go for approximate model. In that approximate model, we neglected the output admittance and the reverse voltage gain HRE parameter. Hence, so we neglected the output admittance parameter and reverse voltage gain in approximate analysis. Hence, the simplified approximate model for common emitter amplifier without emitter resistance is like, so the input side, the source resistance, and HI is indicated input impedance, and there is no reverse voltage gain, hence the input impedance is directly connected to this ground potential. And output port, we remove this output admittance, hence HOE is removed. That is the reason the collector current is directly equal to HFE times of IB. And the voltage is measured, output voltage is measured across the load resistance. So from that, we derive this is the equivalent generalized model for a amplifier. This is the base terminal, and here it is represented as HIE, and this is current source across this collector. It is represented as HFE times of IB, and this is emitter terminal. So here it allows the base current, that is IB. It allows the collector current IC. So this is the generalized model for approximate analysis. And by using this one, now we are going to add some emitter resistance across the emitter terminal to stabilize the operating point with respect to the DC sources. Hence, for this case, we are going to add the extra resistance. That resistance is called as emitter resistance. Now, we need to observe the input between base terminal and emitter terminal, and output is measured between collector terminal and with respect to this emitter node. So for this case, we need to add a source resistance as well as a load resistance to define in a small signal model. Hence, here I am going to show you the equivalent, the small signal model for common emitter amplifier with a emitter resistance. So let us consider, so starts from the source. This is the Vs is the Vs, and the positive pole of this Vs is connected to source resistance, that is Rs. From this Rs, it is connected to Hi, and means if we observe this one, let us consider the generalized model for approximate analysis. So means this is base is connected to Hi, and this is the node, and current source HFE times of IB. This is collector terminal, and across this one we are adding the emitter resistance, that is RE. Hence, the another end of this input impedance should be connected to emitter resistance. Also, on the output side, collector terminal. So let us take this is the collector terminal. The collector terminal is passing through current source. The current source is represented as HFE times of IB, and these two are meeting at the emitter resistance node. So hence HIE and HFE times of IB, these two are meeting at the emitter terminal, and emitter terminal is biased with a emitter resistance that is represented as R. And output side, we need to place a load resistance that is ZL, and the input side we need to place a source resistance that is RS along with a voltage source is VS. The same circuit here I drawn in terms of small signal model. Hence it shows that HIE and a current source is HFE times of IB, and across the emitter terminal this is emitter terminal. Across the emitter terminal the emitter resistance is R. Now we need to identify that how much current is the flows across the emitter resistance. Now we know that from the construction of the transistor, the emitter current is represented as the summation of base current and collector current. Let us assume the base current is represented as IB and the collector current from this equivalent circuit. So let us take this is IC. The IC is represented as, from this circuit, we know that IC is represented as HFE times of IB. So hence this is HFE times of IB. If IB is a common, it is represented as 1 plus HF. So hence the emitter current is represented as 1 plus HFE times of IB. So this amount of the current is passing through emitter resistance, that is R. Now by using this common emitter amplifier with emitter resistance, now we are going to observe the parameters like current gain, input impedance, and voltage gain. Now coming to the current gain for this common emitter amplifier with emitter resistance. If you want to define a gain parameter, it is defined as it is a ratio of output parameter to the input parameter. Now we are going to define the gain in terms of current. Hence, it is defined as it is a ratio of output current to the input current. Hence, from this case, we know that the output current means the current flowing across this load impedance is represented as IL. Means either the load current or that is equal to collector current, but across this load resistance, the flow of direction is opposite direction. Hence, IL is represented as minus IC. So here is not a negative magnitude. This sign indicates the flow of direction of the current across the load resistance. So from that, we defined as the current gain. It is a ratio of output current to the input current. So from this circuit, the output current is represented as IL and the input current is represented as I. So we can write this output current is exactly approximately equal to minus IC, hence minus IC. I1 is represented as I. Now we need to find out how much collector current is the flows. So we know that from the circuit, this collector current is represented as HFE times of I. Now we can substitute here. So means AA is equal to minus HFE times of IB by IB. Hence this IB is a get cancelled. The current gain in this common emitter amplifier is represented as minus HFE. So hence, so the current gain for this common emitter amplifier with emitter resistance is represented as minus HFE. Means there is no difference, there is no change in a current gain in a common emitter amplifier without emitter resistance and with emitter resistance. Similarly, we need to calculate the input impedance from this common emitter amplifier with emitter resistance. And we know that the input impedance is defined as it is a ratio of input voltage to the input current. Hence, from that, the input voltage is represented as V1 and the input current is I1. But by using the circuit, so we need to write the VI means V1 means VI, I1 means we need to write the input current. So from the common emitter configuration, base is acts as the input terminal. Hence, the current flowing across the base terminal is represented as IB, that is acts as the input current. So hence, I represented as, so I1 is replaced with IB. Now we need to calculate what is the V1. So means V1 or VI, V1 or VI. So if you observe this one, if you apply the KVL loop analysis for this side input loop, so the voltage drop across this input impedance is represented as IB times the HI. So hence IB times of HI plus the voltage drop across this. So this input voltage is also passing through emitter resistance. Hence the voltage drop across this emitter resistance is represented as IE times the R. But we know that IE is represented as 1 plus HFE times of IB. Hence, the V1 or VI is represented as IB plus HI, IB times of HI plus 1 plus HFE times of IB into RE. So this IE is replaced with 1 plus HFE times of IB. Why? Because of that, we know that IE is represented as the summation of base current and collector current. So IB is IB. From this circuit, if you observe the collector current is represented as HFE times of IB. So from this, if IB is a common, that is 1 plus HFE times of IB, that is equal to I. Hence, IE I written as 1 plus HFE times of IB. So from this, if you take this IB is a common, so means this is HIE plus 1 plus HFE times of RE, that is IB times of I. So now I'm going to substitute this value in this case. So HIE times of IB plus 1 plus HFE times of IB times of RE by IB. To simplify this one, so from this term, I taken IB is a common term. Hence, from this product, if IB is a taken common term, HIE plus, and from this, the common term is 1 plus HFE times of RE. So then this IB is a get cancelled. So from this, we can say that the ZI is HIE plus 1 plus HFE times of RE. But in a common emitter amplifier, without emitter resistance, we observe the input impedance is that is equal to only Zi or HIE. But in a common emitter amplifier with the emitter resistance, while adding the emitter resistance, it also increases the input impedance. If the input impedance is increases, means it controls the change in base current at the input side. So due to this increase of input impedance, it reduces the base current. So hence the collector current is also reduces. Means the how much collector current is increases with respect to the increase of the biasing voltage, that should be compensated by increasing of this the input impedance at the input side. Hence it controls the base current. Due to this controlling of the base current, the collector current should be compensated. So hence it makes the Q point or operating point is stable. Now we need to calculate the voltage gain. So by using this common emitter amplifier with emitter resistance, we need to calculate how much voltage gain is produced. So from this, we know that it is defined as output voltage to the, it is a ratio of output voltage to the input voltage. Hence, and from this, the current voltage gain is represented as from the circuit. V2 means this is actually the V2. So V2 can also write VC. And input voltage means here that is base voltage, hence I represented as V. And from this, we know that the VC means, so across this load resistance or load impedance, it allows the load current. Hence, VC is represented as IL times the ZL. From the current gain definition, AA is represented as it is a ratio of low output current to the input current, that is IL to the I1. From this equation, IL is represented as AA times of I1. Hence, the VC is represented as, so this IL should be replaced with this term, means that is AA times of I1 into Z. So, so that is the reason. What we observe here, the VC, we observe that AA times of I1 into Z. So from this, AA and I1 means from this representation, the input current means your base current. So I1 is replaced with IB and ZL is the ZL. Hence, the VC is represented as AA into IB into ZL by VB. So if you observe this factor is nothing but it is a reciprocal of, means this is nothing but a admittance. So IB by VB ratio is nothing but a input admittance. So if you want to write in terms of impedance, you can write the reciprocal of impedance. Admittance is nothing but a impedance parameter. So hence I am going to write this is the AA. This factor IB by VB, I am writing the reciprocal of impedance. The reciprocal of impedance is nothing but a admittance. Why? Hence, so this is a admittance, input admittance. Hence, this factor I replace it with reciprocal of input impedance 1 by Zi. So this 1 by Zi is nothing but IB by VB, and the ZL is the ZL. Now we need to substitute Zi parameter, what we observed. So from the input impedance, we observe that from the input impedance, we observe that Zi is represented as HIE plus 1 plus HFE times of RE. Now I'm going to substitute this input impedance in a voltage gain. Hence, so now I'm going to substitute. So that is, so again I'm going to substitute this AA value also. From this approximate model, AA is represented as minus HFE. And ZA is represented as HIE plus 1 plus HFE times of RE. These two parameters I am going to substitute in this voltage gain. So from this circuit, we observe that the voltage gain in a common emitter amplifier with emitted resistance is represented as A times the ZL by ZA. And by using this approximate model, we observe that the current gain for this common emitter amplifier with the emitter resistance is represented as minus HFE, and the input impedance is represented as HIE plus 1 plus HFE times of R. Hence, I am going to substitute these two parameters. AA is replaced with minus HFE, ZL is a ZL by ZA is replaced with HIE plus 1 plus HFE times of R. Now, in this case, let us consider, and with respect to the common emitter amplifier without emitter resistance and with emitter resistance. In a with emitter resistance for a CA amplifier, the input impedance is increased. Hence, let us consider 1 plus this, in this case 1 plus HFE times of RE is much greater than of HIE, and let again assume the HFE parameter is much greater than 1. So what happens here? We assume this parameter 1 plus HFE times of RE is greater than of HIE value, and HFE should be greater than of 1. Under this condition, we can neglect this input impedance. So if we neglect this input impedance, this AV becomes approximately equal to minus HFE by ZL by, if HI is neglected. Why HI is neglected means we assume that this 1 plus HFE times of RE is greater than of HIE value. Hence, this is becomes 1 plus HFE times of R. So, under this analysis, HFE by, so I'm writing like this, minus HFE by 1 plus HFE into ZL by R. So, if you observe this ratio, HFE by 1 plus HFE is approximately equal to unity factor. HFE by 1 plus HFE is approximately equal to unity factor. Means, so by using this, by adding this common emitter, means emitter resistance, it stabilizes the voltage gain. So from this emitter resistance, it stabilizes the voltage gain. Hence, with the voltage gain it stabilizes, so the Q point is also becomes stabilized. So that is the reason. This factor IV consider that is approximately equal to unity value. Hence, AV, the voltage gain is approximately equal to ZL by R. Hence, so that is approximately equal to ZL by RE value. So means it depends upon the load impedance and so how we are going to stabilize this voltage gain with respect to this adding the biasing resistance. Means it is not, this voltage gain is not depends upon the small signal model parameters. It depends upon only the emitter resistance and load resistance or load impedance. By using this factor, we can stabilize the voltage gain to make the Q point is stable. So up to this point, we observed the common emitter amplifier with a emitter resistance using low frequency model. We'll discuss one problem for this case. Let us consider a common emitter amplifier uses load resistor, that is RL is a 2 kilo ohms in the collector circuit and is given by the voltage source Vs of internal resistance is 1000 ohms. For this case, given the H parameters, the H parameters of the transistor are HIE is 1300 ohms, HRE is 2 into 10 to the power of minus 4, HFE means current gain, the current gain is 55, and HOE is 22 micromos, that is ohm inverse. Neglecting the biasing resistors, compute the current gain, input resistance, voltage gain, output resistance, and output terminal limits, that is the total resistance. For the following values of emitter resistor, RE is inserted in the emitter circuit. Let us consider the two different cases. What happens? We need to see if the emitter resistance is added. In the one time, we need to consider the emitter resistance is 200 ohms. And another time, we need to consider the emitter resistance is 400 ohms. And use the approximate model for the transmitter if permissible. Means, first we need to find out that we need to choose either the exact model of common emitter amplifier with emitter resistor, or we need to use the approximate model of the common emitter amplifier with emitter resistance. So before going to identify which type of model we need to use, so we need to verify the condition from that approximate model analysis. We know that this HOE times of ZL value should be less than of 0.1. Then we go for approximate model. So for a common emitter amplifier without emitter resistance, we observe that for approximate analysis, HOE times of ZL value is less than of 0.1. Then we go for approximate model. But for this common emitter amplifier with emitter resistance, we need to choose this HOE times of along with the emitter resistance, means RE plus ZL value is less than of 0.1. Then only we can go for approximate model. Otherwise, we need to choose the exact model of common emitter amplifier analysis. So before going to this, first we need to identify what are the parameters are specified. So in this problem, they specify that the load resistance is 2 kilo ohms and internal resistance means the source resistance. The source resistance is 1000 ohms And H parameters are HIE, they given that HRE and HFE and HOE. Now we need to calculate, current gain, and that is AI, input resistance either RI, or you can also write ZI, input impedance, voltage gain AV, output resistance R0, and the total output resistance R1. So for this case, let us consider these are the given data from the specifications. RL load resistance is 2 kilo ohms, RS is 1000 ohms, and HI is a 1300 ohms. HRE is 2 into 10 to the power of minus 4. HF is a 55 and HO is 22 micromos. So first we need to identify that which model we need to choose, either the exact model or approximate model. So if you want to choose approximate model, the parameter HOE times of ZL in a normal common emitter amplifier without emitter resistance means HOE times of ZL is less than of 0.1. This is for CE amplifier without emitter resistance. Means in this case, emitter is directly connected to the ground potential. But if we consider the common emitter amplifier with emitter resistance, we need to verify this HOE times of ZL along with emitter resistance value is less than of 0.1. Then we go for choose the approximate analysis. Hence, for the first case, let us consider the RE value is 200 ohms. Now we need to identify that we need to choose exact analysis or approximate analysis. To identify this case, we need to verify this condition. HOE times of ZL plus RE should be less than of 0.1. Then we go for approximate model. Otherwise, we go for exact model. Hence, I am going to verify this one. HOE means, what is HOE value? 22 micromos means 22 into 10 to the power of minus 6. And this is RE means, they given that RE is 200 ohms. ZL or RL, both are same. Output impedance, load impedance. So RL is also load resistance. So hence the load resistance is 2 kilo ohms means 2 into 10 to the power of 3. If we solve this one, it gives that value is this product value is HOE times of emitted resistance and the load resistance is gives 0.0484. So from this, what is the condition? HOE times of ZL plus RE is less than of 0.1. Then we go for approximate model. So this value is always less than of 0.1. That is the reason we can choose a approximate model. So from this approximate model, we need to determine the current gain, voltage gain, input impedance or input resistance and output resistance. Hence, first I am going to calculate the current gain from the approximate analysis. Just now we observed that for this common emitter amplifier with emitter resistance, the current gain is represented as minus HFE. Means, so this minus HFE is directly given the problem. So value is 55. Hence, the current gain is represented as minus 55. Now we need to calculate input impedance. From this approximate analysis, we observed that the input impedance is represented as HIE plus 1 plus HFE times of R. Now you can substitute the values. HIE value is 1300 ohms, means this is 1300 plus 1 plus HFE value is 55, and RE, this is RE value we need to consider 200. So means this is 1300 plus 1 plus 55 means 56 into 200. If you solve this one, it gives that the input impedance is 12.5 kilo ohms. The input impedance value is 12.5 kilo ohms. Now we need to calculate the voltage gain for this emitter resistance is 200 ohms. So from that approximate analysis, the voltage gain is defined as AA times ZL by ZI. So here you can substitute AA means minus HFE. So what is the minus HFE value? This is minus 55 into ZL means the load resistance, that is 2 kilo ohms means 2000 by ZI. Just now we observed the ZI value. So ZA is observed 12.5 kilo ohms. We need to consider this value. Hence, that is 12.5 kilo ohms means 10 to the power of 3. Now you can solve this ratio. It gives the voltage gain for this common emitter amplifier when the emitter resistance is 200 ohms, that is minus 8.8. So this is voltage gain when RE is 200 ohms. So similarly, we need to calculate when the second case when emitter resistance is changed from the 200 ohms to 400 ohms. And before that, and we need to calculate the output resistance. So in approximate analysis, we consider that the output impedance should be very, very high. Means 1 by HOE should be much, much greater than of ZL. Then only the parallel impedance is approximately equal to load impedance. From that, so in this approximate analysis, we observe that the output resistance should be very large. Here we consider as infinite. But and based on the circuit, if you want to calculate the total terminal resistance, and from the terminal resistance, the output impedance should be parallel with the load impedance. So hence ROT is represented as RO is parallel with RL. And in that approximate analysis, we consider as your output impedance should be very large and RL is 2 kilo ohms. If the two resistances are unequal and the parallel resistance always gives it is smaller resistance. So in this representation, output impedance is a very large and RL is a 2 kilo ohms, hence the total parallel impedance is approximately equal to RL value. So from this, the RL means they given that 2 kilo, hence the ROT value is 2 kilo ohms. Now we'll see what happens when RE is 400 ohms. So now again, with respect to this emitter resistance, now we need to first find out that which model we need to use. Either exact model we need to use or approximate model we need to use. To identify this one, first we need to verify this condition. HOE times of ZL plus RE, it should be less than of 0.1. Hence, I am going to verify this condition. The HOE value is 22 micromoles, means 10 to the power of minus 6. RE, now we need to consider, in the previous case, we considered that RE is a 200 ohms. Now we need to consider RE value is a 400. So 400 plus RL is 2 kilo ohms, means 2 into 10 to the power of 3. So if you solve this ratio, it gives the factor, this HOE times of RE plus RL is equal to 0.0528. Now it should be, we need to compare with this condition. What is the condition? HOE times of ZL plus RE is less than of 0.1. Then you can choose approximate model. And based on the given specifications, the HOE times of RE plus ZL is less than of 0.1. Hence, we can choose the approximate model for this common emitter amplifier with emitter resistance. Hence, now by using this approximate model for a common emitter amplifier with emitter resistance, now we are going to calculate the parameters like current gain. So first, current gain from that approximate model, the current gain is represented as minus HF. Means, so in a current gain is the current gain for this common emitter amplifier with emitter resistance. Current gain is not affected with respect to the emitter resistance. Hence, so without emitter resistance or with emitter resistance, the current gain is the same. Hence, A is represented as minus HFE. So the HFE value is 55 and this is minus 50. So now we are going to calculate the input impedance ZI from this approximate analysis. ZI is represented as HIE plus 1 plus HFE times of R. Now you can substitute this HIE value is 1300 ohms, 1300 plus 1 plus HFE is 55. Now RE value is 400. So hence this is 1300 plus 56 into 400. If you solve this ratio, it gives the input impedance is 23.7 kilo ohms. The input impedance is 23.7 kilo ohms. But if you consider without emitter resistance for a common emitter amplifier, the input impedance is equal to HIE parameter, that is only 1300 ohms. But while adding this emitter resistance, it increases the input impedance. Hence, from this, the input impedance is represented as 23.7 kilo ohms. Now we need to calculate the voltage gain. So AV, so that is equal to AA times of ZL by Z. So AA means we observe that AA is equal to minus HFE, that is minus 55. And just now we observe the ZI value is 23.7 kilo ohms. So hence ZI value is 23.7 kilo ohms. Now we can substitute this one. AA is minus 55 and the ZL value means the load resistance value. That is 2 kilo ohms, means 2 into 10 to the power of 3 by ZI value is 23.7 K means into 10 power 3. So from this, the voltage gain is represented as minus 4.654. Now we need to calculate the ROT parameter. So for this case, let us consider the output impedance is very large for this approximate model. Why? Because of that 1 by HOE is much greater than of ZL. From this analysis, we assume that the output impedance is very large, and here I consider as infinite. So from the circuit, if you want to calculate the total output terminal resistance, that is parallel with the output impedance is parallel with the load resistance. Hence, R0 is parallel with R0. So here I consider this R0 is infinite, and it is a parallel with RL is 2 kilo ohms. So in a parallel configuration, if the two impedances are unequal and the parallel resistance is used with smaller resistance. Let us consider if R0 is a very large and the load resistance is a small resistance. And from the circuit analysis, means from this your small signal model, the output impedance and the load resistances are parallel combination. Hence, by using this parallel combination, the parallel resistance is equal to smaller resistance. So hence, from this observation, we observe that output impedance is a very large and the load resistance is a 2 kilo ohms. Means, so this factor 1 by HOE should be much greater than of ZL. So that is the reason R0 is much greater than of ZL value. By using this assumption, this parallel resistance ROT is approximately equal to RL value. Hence, at this point, the total output terminal resistance is equal to load resistance, that is equal to 2 kilo ohms. So up to this point in this today's session, we observed that the common emitter amplifier with emitter resistance using small signal model or a low frequency model. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.